Okay, welcome back to the class. So we will continue with this example, but now we want to use the more finite state machine to design the same circuit. Okay, so instead of using the uh, milli-state machine, so now we will use the more state machine. So how to do that? So we need to go back to the fundamental where we will look at um, the process of adding numbers in digital. So we look at here we have the truth table of a full adder. Again, we have this, and we have C in input, we have A and B, we have sum and also the C out. Okay, so we have 0, 0, 0, 0, 0, 1, 0, 1, 0, and 1, 0, 0, number 4. And we also have number 5, number 6, number 7. And for 0 plus 0 plus 0, we have sum equal to 0 and C out equal to 0. 1 here, 0. For this 1 here, we have 0. And this also 1 here. We forgot number 3, right? So after number 4, we should have number 3, which is 0, 1, 1. Okay. So for number 3, we have this 0 and we have C out equal to 1. Yeah. Here we have S equal to 1, C out equal to 0, and it's 0 equal to 1, and 0, 1, and here we have 1 and 1. Okay. Now, from here, we can have two sections where if we observe this, we can see that here we have C in, where C in equal to 0 for this part. And for the second part here, we can see that here C in equal to 1. Okay. And to have the more state diagram, so we need to have the output, which is the S. S is our output, should be inside uh, the state, right? So let's have the first state. Okay, so and again we have two two section, right? Two section where we can say that our G is when we have no carry in or carry out. We have H where we have carry in and we have carry out, right? And for the first state here is state G, and now state G, we cannot only have one state for G, because for more state diagram we need to have output inside the state, and we can see that for this part, all right, we have two possible output here, which is s equal to 0 and s equal to 1. All right, so we need to have for state that no carry in and no carry out, now we need to have two states. So let's name this as G0, where s equal to 0 in this case. All right, and we can have the second one. Let's name this as G1, where s equal to 1. So now for the condition that we have no carry in and carry out, which is this one, all right, this part no carry in, right, we can have two conditions, where the first one is when s equal to 0 and the second one is when s equal to 1. Also the same as this one, we have two conditions where s equal to 0 and also s equal to 1. So for h also we need to have two states, right? So we have h0 where s equal to 0, and also we need to have h1 where s equal to 1 in this case, right? So we need to have at least four states now. Okay, and how the state, how we transit between one state to another state. So we need to look at the input A and B, all right? So for example here, when AB equal to 0, 0, and we can see that we don't have C out, so we should stay here. But if 1, 1, yes, S equal to 0, but we have C out, so uh, we should go H0, right? Because S equal to 0, and here is the condition where we have the carry, right? So we can say that if right, AB equal to, this is AB equal to 0, 0, we should stay here 0, 0, right? AB equal to 0, 0, and our S should be equal to 0, and we don't have any carry out, so we should stay here. But if AB equal to 0, 1 or 1, 0, we can see that S should be equal to 1, and we don't have carry out. So we cannot say stay here because S now should be equal to 1. So we need to go to state G1. So if input is 0, 1 or 1, 0, A and B, 0, 1 or 1, 0, we should go to state G1. All right, based on this. And the last one, when we have 1, 1, and we can say that we have C out now, and we don't have or S equal to 0. So we have C out, so we cannot stay here or here, but we need to go to H0. So in this case, if 1, 1, we should be here. All right, so this is the possibilities. These are the possibilities if we are in G0, all right? So if 0, 0, we should stay here. If 0, 1 or 1, 0, we should go to G1. If 1, 1, we should go to H0. Okay, so now let's look at here, G1. When we are in G1, so if 0, 0, what we should do? If 0, 0, 0, 0, and of course G1, we don't have any C in. If 0, 0, C out should be 0 and S should be 0. So this is the state that C out is 0, S is 0. So we should go back. 0, 0, 1, 0, 0, 1 or 1, 0, we can see that S equal to 0, S equal to 1, and C out. We have no C out. All right. So we should stay here. So 0, 1 or 1, 0, we should stay. Okay. We should stay. And what about 1, 1? If 1, 1, we can see that S equal to 0 and we have C out. Where is that? Here. So if 1, 1, we should go here. 1, 1. Okay. So it should be done for G1 because we have 0, 0 already. 0, 0, you need to go back to G0. And for 0, 1 and 1, 0, we should stay at G1, and 1, 1, we go to H0. All right, should be done for G1. What about H0? And H0, we should look at this part because we have C in H0 and H1. All right, so when we are 0, 0 at the input, 0, 0, so what should we have? We have S equal to 1, right? S equal to 1 and C out equal to 0. So no C out. So where is S equal to 1? Here, and no C out should be this state. So if 0, 0, we should go back to here. 0, 0 should here. What about 0, 1 and 1, 0? Should go to the same state, right? But what is the state? So look at here. So we have 0, S equal to 0, which is this one or this one. But because we have C out, right? So this is the state that we have C out, right? So if 0, 0 and 0, 0, 1 and 1, 0, we should stay here, all right? 0, 1 or 1, 0, we should remain here. Okay, what about 1, 1? 1, 1, we have C out, so either this one or this one, but look at S equal to 1, so it should be this state. So if 1, 1, we should go to this state, right? So it should be done for H0 because we have 0, 0, go to G1, 0, 1 or 1, 0 remain at H0 and 1, 1, we go to H1. It should be done here. And the last state, right? So if 0, 0, all right, 0, 0, we have as equal to 1, all right, and we don't have C out. If don't have C out, so either this or this, but we have as equal to 1, so should be this one. So if 0, 0, we should go to here, 0, 0. But if 0, 1 or 1, 0, so we have, yeah, we have the C out, so should be this 2, but as equal to 0 should be this one. So it should be 0, 1 or 1, 0 should be this. Go back to H0. But what about 1, 1? 1, 1 we have C out, should be this 2. And as equal to 1 should be this one. Okay. So 1, 1. So we have 0, 0. We have 0, 1, 1, 0. Go back to H0 and 1, 1 stay at H1. So this will be the state diagram, the complete state diagram of the our finite state machine. All right. So now we need to have our block diagram of our finite state machine. All right, for this. Yeah. So to do that, easy, because we always know that the general uh, block diagram of the Moore state diagram must be something like this. We have the state register, which is the flip-flops, and we always have the output logic, and we will have the next state logic. Yeah, so this will be the our next state logic. This is the state register. This is the output logic, right? And the state register, of course, you need to have the D and Q because this is flip-flops, and you have the clock, all right, and this should be input from the next state, and this should drive the output logic, and your output should be S, right, based on this S. What about your input here? Should be A and B, right? Your input A and B. Okay, and remember you need to have the feedback, this to this, right? Do you need the feedback from not feedback, the input here A and B to drive the output logic? No, you don't need that, because that one is for milli, right? This one is for more state diagram, so we don't have to drive the output logic from the input, right? Now the question is, what is the size of our state register? How many bits? So we need to look at our state diagram. So our state diagram, we have how many states? We have 4 states. All right, so 4 states, you need to have at least 2 flip-flop or 2 bit here. All right, because 2 power of 2, 4 state. All right, exactly. Okay, so this is the state FSM circuit, finite state machine circuit for our this. So to write the code is your homework. All right. So your homework is to write the code for this one. I just give you the simulation. Um, you can use the same. Actually, you can use the same attachment for the more FSM. Yeah. The only difference is the size of no different. The only difference is in here, right? So this should be the same, right? This should be the same. This should be the same because the register is still the same. But here you have G0, G1, H1, H0, all right? And the size of your next state and state is 2-bit now, all right? The others should be still the same, not that difficult actually. So uh, so maybe all right. So I have one. I just want to show you the simulation result and see the attachment is the same. All right, same value, and let's try to simulate this. Okay, so this is the result, and now the our sum is here. So make it okay. Put it here so that we can see A is 3 and B is 4 is loaded into the register here and it's shifted here, but the output here is, look at here, 1 2 3 4 clock cycle also. All right, and we can have uh, for number 7 here, 3 2 plus 3 3 plus 4 is 7 after 4 clock cycle. But what is the difference? If we look at the output for more and milli, so let's open the milli one. And let's see the difference. Okay, should be this one. Yeah, this is the milli output, and sum is here, so bring it to here. And where is the more one? Is it one? Okay, so all right, so when we can compare between the two, So this is milli and this is more. The observation, we can see that the output for the more is slower uh, as compared to milli, where we have the output here earlier one clock cycle here. All right. Okay, we can see that the output is immediately available here for milli, but for more, one clock cycle delay here. All right. So that is because of the circuit design of the more and milli is this. When we look at the milli, we have this signal, means that the output at Z is available immediately after the W is changed. All right, just like these described, just like described in the state diagram, we can see that the output is available immediately when the state is changed from A to A or A to B. So we can see that this is available immediately. Whereas in more, we can see that the output is only available when the state is or inside the state. All right. So yeah, we can see that. Right. The milli is available immediately here. Okay. The first add 1 plus 0, you have 1. Here 1 plus 0, the output is delay 1 clock cycle. Right. So but you have 1 clock cycle only delay, and also if you look at the advantage of milli is of course um, the size of the circuit. But the drawback of milli is that in some design you need to design carefully because of the glitch problem. So if you want to know that, so you can look at this example. All right, try to do this and try to simulate whether you can get the correct output or not because of the glitch problem. You can see uh, the output of this one is not that good as compared to the more one because you may have a false signal or false output. All right, what we call a glitch, that it's a very short time the signal is the one that we expect is 0. For example, we expect 0, but in a short time the signal go to high. All right, so that can happen in milli state model. So we need to be careful if we use milli state model. But if our output is loaded into the register like this, we not immediately read the output from the finite state machine, then the output should be okay. It should be glitch free. All right, that's why here we can see that the output is quite smooth, clean. All right, there is no glitch. Okay, but if we read the output immediately like this, yeah, that is from the finite state machine, so you may have problem with the Z. You can try to design this in Verilog and try to simulate. You can see that problem. Okay, so that will be the this the serial adder, and remember you need to do this. Yeah, write the code for this and try to simulate as your homework. All right, not the assignment. Yeah, the homework. Okay, any question? All right, so if no question, we will proceed We need to finish this chapter by today, and next week we will go to the next chapter, which is the RTL design, where we will learn how to apply what we have learned here: finite state machine, the sequential circuit design, and combinational design, all right, to create bigger circuit as compared to this, right? For example, when we want to design a processor, you need a processing circuit. So how to do that, right? So now we continue with this one and look at what we call an algorithmic state machine, or ASM, right? So actually, algorithmic state machine is the same as FSM, finite state machine. The only difference is that we now draw the state diagram in the form of flow chart, rather than using the this style of representation. Now we represent the state transition of the state and the transition of the state in the form of flowchart. So this, for example, the state, all right, rather than using the circle, so now we use the square box like this to indicate that this is the state. And for the condition, whether the condition is true or false, just like you did in designing computer program, in computer programming, right? You write the flowchart. This is the condition, all right? So the box is the diamond shape like this, where if the input and you ask for the condition, whether the condition is true or false. So for example, if false, you go this way, and if true, you go this way. So this is a condition expression, if else. Uh, and for Mealy type, between the transition, so if you have the output, you can have this to indicate the output, all right, conditional output box. We will see the example later. All right, for example, back to our first example here, where we have the automated speed regulation, regulated vehicle. Where is it? This, okay, where if W equal to 0, we stay at state A. If W equal to 1, we go to B. And at B, if W equal to 1, we go to C. And if 0, we go back to A, and so on and so forth. Right now, we change this to the flowchart, right, to the ASM. So we can have something like this. Okay, now at state A, okay, this is state, remember, state, right? State A. So when W equal to 1, we go to state B. So W now is our decision, right? The input now is the decision, because um, uh, the transition of the state is depend on W signal. So if W equal to 1, we go to B. But if it is equal to 0, we remain at state A. Just exactly what we have in state diagram. All right. But in B, when W equal to 1, we go to state C, right? And state C, we have Z inside, means that Z equal to 0. Here, if you write nothing here, means that Z equal to, sorry, if you have Z equal Z here, means that Z equal to 1. And if you don't have Z here, means that Z equal to 0. Or you can write inside here, Z in this state, Z should be equal to 0, Z should be equal to 0, and here Z equal to 1 in state C. All right. But when we are in B, if W equal to 0, we should go back to A, right? Yes. Okay, and in C we see that if W equal to 1, we remain at C, all right, just like what we did in the state diagram. But if it is equal to 0, we go back to state A, all right. So this is the ASM chart for the first example, and this is for more machine, more state machine. For the milli machine, all right, we have two state, remember, so A and B, and if W equal to 1, we go to B, but if W equal to 0, we go back to A. And actually we need to have the output here, but to make it simple, if the output is not activated, so just stay like this, means that here Z equal to 0, yeah, Z equal to 0. But look at B, when we are at B, right, when W equal to 1, this means that Z equal to 1 here. So this is output of the milli, right? Z equal to 1, and again, if still 1, so Z equal to 1. But in B, if W equal to 0, we go back to A, just like in in state diagram, right? So this is the ASM. That's it. So what is the why we have ASM? The reason is that this one, using the state diagram like this, if we have a small number of states, for example 3, 2, 5, 4, 6, all right, there should be no problem to use FSM state diagram like this. But if you have many states, all right, many states, and you have many signal to consider, input you have many signal, output you have many signal, so the best way is to use ASM, flowchart. Just imagine if you have many signal and you have more than 10 states, so to use the state diagram is too complicated, all right, as compared to ASM. So that's why ASM is better if you have a more complicated finite state machine. All right, now let's look at the example number 3. Okay, so for example number 3, and should be the last example for this chapter. So in a computer system, usually contain a number of registers and hold data during various operations. Yes, we learned this already in computer design, in microprocessor system. All right, that in microprocessor, for example, we have many register, right? We have register. For example, if you use ARM microprocessor, the one that is in your iPhone, in your Android phone, yeah, you have register number 0, you have register number 1, R0, R1, R2, R3 until R15. All right, that is the general purpose register. Um, and this register is used to hold data during various operations, right? So for example, you want to add number, so the data must be in the register first, before you send to the adder, and again the result must go back to the register, right? So for example, uh, you want to add two number, okay, so you have three register, for example. Okay, let's name this as R0, this is R1, or R1, R2, R3. So you want to add data in R1 and R2, and the result is stored in R3. All right, so you need to read the data from R1, R2, all right, through the bus. Okay, so for example, our system is 8-bit. So you have 8-bit bus, 8-bit bus, and you put in the ALU, for example. All right, so this one is for this one is for this, and the output is go to R3. Right, so that is the operation in the computer, for example. Okay, so sometimes it is necessary to swap, all right, the content of two registers. Typically, this is done by using a temporary location. This is usually a third register. So, for example, your operation is not add, like what we have here. So, for example, we want to do something like this, yeah, rather than add, we want to swap a data from this. For example, if this is one, for example, we have x and y, all right, and we want to swap the data between the R1 and R2. Okay, so what we do is that we need to bring this value to R1, and in computer, if you do that, what happens is that you will replace this R1 to this R1, this X, where we have X previously. When we bring this Y from R2 to R1, you will you will overwrite the value inside, or replace the value inside R1. So we don't want that. All right. So what we should do is that, yeah, we should have, for example, copy this X to the third location or third register. So we copy this X to here, so that later on we can now copy this Y to X, so that we have Y here, and after that we copy this X to R2. So now we can swap the data, but you need a third register, all right, to temporarily store the value, to avoid any data that to get replaced by the another data. All right, so that is how the computer work, when you swap the data. All right, but how to design the controller to do that? Okay, so this is how. Okay, so same thing. For example, suppose that we want to swap the content of register R1 and R2. We can achieve this by first transferring content of R2 into the third register, R3. So in this case, we from R2 we save in R3, and next we transfer the content of R1 into R2. Yes, and finally transfer the value of R3 back into R1. Right. So same thing. So we want to do this, the control circuit, uh, to do the swap, the data between R1 and R2. All right. So we need to have this signal R1 out, to read value from R1, R1 in to write the value into R1, same as this one, R2 out to write to read the value. Actually, this is the signal. Yes, R1 out to the signal that used to read the data from R2, and R2 in is to write, same as this one, R3. Okay, so we want to produce this signal at the right time. Okay, so what we can do is something like this, the state diagram, or we can have the ASM chart like this. So for example, uh, when we are at state A, all right, and if there is no start signal, in this case the start signal is W, means that if W equal to 1, we do the operation. If W equal to 0, we not do the operation, right? So when reset, we are in state A. And if we start the operation when W equal to 1, so what we do is that we want to read the content of R2, all right, and put into R3. Yeah? So this, what we do is that, yeah, maybe we can use this. All right. So for this case, what we do is that from here we have R2, and here we have R3. What we do is that, for example, in R2 we have X. So we read R2 out, means that we read from R2 and we write to R3. So R3 you have X in this case. And of course you have the R1. Okay, so let's, for example, initially R1 you have Y. So you copy the content of R2 to R3 in this state. And next here R1 out means that you read from R1 and you store in R2, R2 in equal to 1. Right? So from here Y you bring to here. So you can have your Y here. Y here in this state. Now the next one is the last one where you read from R3 and put it in R1. All right, so from here, from R3, bring it to R1. Oops, so you have here is X. Yeah, now you swap the data between R1 and R2. And you have one signal to indicate that the process is done. So signal done equal to 1 when the swap operation is finished. All right. Again, I repeat. Yeah. So let's, for example, we have R1 and R2. So let's change a little bit so that easier for you to understand this. R1, R2, R3. So let's, for example, we have X in R1, Y in R2, right? So what we want is we want to swap the data between R1 and R2. So we want at the end, we will have something like this. Inside R1, we have Y. Inside R2, we have X. Right? Swap. Okay, that this is what we want. So what we need to do is that first, yeah, here we read R2 to save the content of R2 because we want to replace R2 with X, right? Remember? So we need to save the content of R2 into R3. So this is what we do, R2 out, all right, to read, and R3 in, to write to R3. So from R2, we bring this to R3, all right? Now we have something like this for the first operation, the second state here. And here we read from R1 and replace the content of R2 with X. Here, R2 in equal to 1. So after we do that, we can have X here for this. And the last one, we read from R3 and put it in R1. So we have our Y here. Right, now we swap the content of R1 and R2 already. Right, and we have the done signal here to indicate that the the process is done, is finished. All right, and we after that we go back to wait state. All right, if w equal to 1 again, we do again. All right, if w equal to 0, we stay here. So that will create this control circuit. All right, so we can do that also in the form of ASM chart. All right, so this is the state A, no transfer. If w equal to 0, we remain here. If w equal to 1, we do this. And the state transition, yeah, from B to C and C to D and D to back to A, we don't have to wait W. All right, so means that once we go to this state, we need to finish every clock cycle. The next clock cycle we do this, the next clock cycle we do this. No need to look at the input. You see, w equal to 1 or 0, we don't care, we need to go. All right, so this one is the same. All right, R2 out, R3 in for the B, and we go after that one clock cycle, we go to state C and go to state D and go back after that. Okay, so that will be the block diagram, the ASM and the state diagram. So this is how to design the circuit, and just like we did in first example, to design the circuit, so you need to have state table, state assign table, and of course you after that you get the circuit. All right, and it's quite, yeah, time consuming here, and quite complicated when you need to uh, get all the equation for R1 out, R1 in, R2 out, R2 in, and so on and so forth. All right, but when you want to describe using Verilog, you don't need to do that, where you can actually use this and straight away you can produce the Verilog code already. So what you need to do is that, again, you need to have the general description of your finite state machine, the general block diagram, or what we call the functional block diagram. All right, so you can have your block diagram is like this. Again, you can have the state register, the output logic, the next state logic, and you have the right? State register, the flip-flops, you need to have D input and the output is Q. And what is the input for your finite state machine? Here should be the W, right? Okay, because you have this, and this is your input. W, your input. Uh, and what is your output? So the output are many, right? You have how many output? For one register, you have these two output control there. So when we look at this, yeah, these all are the output of your finite state machine, because this is your finite state machine. All right. So you have 6, right? So you will have 6. So your output here, you have 1, 2, 3, 4, 5, 6. You have odd 1, odd 1 in, you have odd 1 out, you have odd 2 in, odd 2 out, odd 3 in, and odd 3 out. And you have another signal actually, which is the done signal. All right. Where is this signal? Not indicated here. Oh, yeah, yes. You see the arrow? This is the done signal. So, again, if we have this, we can design the circuit. And how many bits is this? We have how many states? We have 4 states. So if we have 4 states, how many bits we should have in our finite state machine? 2 bits. And of course, you need to have the feedback from here to here. All right, and this will be your circuit. All right, and you need to define what is inside here. What is inside here? All right, using behavioral modeling. Okay, and again, it is based on this or this. All right. So in this example, the code is not given, and this will be your second assignment. All right. So your second assignment is to design this using Verilog. Okay, and this will end our lecture in this for this chapter. Okay, any question? Right. So today, if you have any question regarding FSM or ASM or how to design or any question, you can ask. Right, before we end the session shortly. If you don't have any question, so we can end the session now. Thank you and see you next week.